Hello and Happy New Year to everyone who's joining us today. Um, if you're coming back for our many journal clubs, welcome again. If you're new, thank you for joining us. And just a small recap, we do this journal club every month towards the last week of the month on a Wednesday or Thursday, and we like to bring in radiologists. Specifically, it was meant for radiology residents and staffs, but has evolved and fellows, but has evolved to a lot of radiologists, and we also have scientists who work in artificial intelligence who join us. So please, please welcome and keep coming back, because I thoroughly enjoy the discussions that we have. So this month we are kicking off the year, I think, with a very interesting journal club, which is reviewing some presentations from the RSNA Pneumonia Challenge. And one thing that I like about this challenge was that for me, I was silently rooting for, especially the radiologists on the teams, because I wanted to see the leaderboard of, led by radiologists, because I think some people always assume it's, we've seen a lot of articles that say we want to replace radiologists, but for me, this was just an interesting perception that domain expertise is still important, and that people can actually do this. We'll hear from people who have day jobs as radiologists who did this and won some money. Maybe they may tell us something interesting with how they spend. No, I'm kidding. We don't need to know how you spend your money, but we do really want to inspire people to participate, because I'm pretty sure this year there is several challenges that will be coming up. So at the end of this presentation, if you have a little bit of insight of how to get involved, how to get started, whom to team with, if you participated in the challenge and you're looking back to see what could I have learned from a presentation, then this will be your chance. So we had 4 panelists, but one of them is not feeling well. The number 1 team, Ian Pan, I think he's still at work, but Alexandra, who's a good friend of mine, will be presenting their winning solution. Dr. Philip Cheng from Kirk School of Medicine, he's an abdominal radiologist, was number 3, and I look forward to listening to his presentation. And Felipe, who's joining us from Brazil, thank you. Was number 10 team, and this was pretty impressive, and we will be listening to his presentation. As usual, please type in your question in the GoToMeeting type of the query button, and I will ask the presenters to answer your questions. And just, winning a Kaggle competition is not easy. You can see there are 346 teams, and you're welcome to just search on Google to figure out, just sort of understand a little bit of how, sort of a little bit more of the data set and what it meant. At this point, we're not going to focus more on, working towards, explaining the data in detail. We've had several journal clubs in the past that sort of go through the ChecksNet data set, which was used for this. And if people want a recap of data, just email me and I can organize for a journal club that is similar. And so I wish to thank everyone who works on the advisory council, but at the same time, invite other people to join in. You may see we have 3 fellows who will be rotating off in 5 months for me as staff, and so technically will not be residents or fellows, and we want new faces. And so if you're interested in sort of running this and organizing this, please reach out to me. And I think it's a fantastic opportunity, and I've really enjoyed working on this. And we are just going to go ahead to the presentations, starting with Alex.
Okay, thank you very much, Judy, and congratulations again for your great journal club. It's very impressive that you keep every month this journal club. So congratulations. So today, I will briefly present our team solution to the pneumonia challenge. Ian Pan is a third-year medical student at Brown University with a very bright future for sure. And I'm a diagnostic and interventional radiologist at Cis-Lanaudière in Quebec, Canada. Also, again, congratulations to all the other teams who participated this year, and thank you very much to the organizers from RSNA, Kaggle, and MD.ai. And a special thank you also to all the annotators who invested a lot of time to re-annotate the challenge dataset. There were like 18 annotators, I think 12 from STR and 6 general radiologists. So thank you very much to all of them. So out from the press, RSNA published today the first issue of a new journal named Radiology AI. It's looking like a great journal in a very fast-moving field. Congratulations to the editor, Charles Kahn, for all the work done in the past year to create this new journal that is really fantastic for the machine learning community in medical imaging. It's also very interesting to mention that there are 2 different articles published just today related to the RSNA challenge. So if you are interested to know more, I would recommend to look at these. There's one about the re-annotation process, and another about the importance of medical imaging competitions in the machine learning field. So there's absolutely no doubt that participating in a Kaggle competition is a very exciting experience, but I must admit there's a small touch of insanity about doing this after work hours as a radiologist or a medical student for Yan. I'm pretty sure many participants were in the same context like Felipe and Philip. But there's definitely also a moment when you consider to simply enter the right truck and push the cruise control button during the competition. Above all, Kaggle is really a great learning platform with a very large community of data scientists driven by open values like collaboration, code sharing, and education. So the task for the competition was to classify and localize visual signs of pneumonia on a chest X-ray with bounding boxes. From a high-level standpoint, we divided this problem in 3 main steps. The first step was to classify the image with a binary or 3 classes classifier to generate a global image score for lung opacity. Then we use different object detection architectures to generate bounding box associated with a local classification score. We then combine the global and local scores into a final score for each detected bounding box. Finally, to adjust for the differences in the annotation process between the training and the test dataset, we made some assumptions to better adapt for this situation. So in more details, the final implementation included a total of 60 models divided in 10 classifiers, models, and 50 detection models trained with different architectures, different hyperparameters, and different folds. We created 5 different ensembles of predicted bounding boxes and averaged the predictions that were above classification thresholds. For domain adaptation, we resized the final bounding boxes and lowered the classification threshold to improve sensitivity. These domain adaptation parameters were mainly tuned on the stage 1 leaderboard dataset. That was the first part of the competition. To force learning from negative images in detection model and to balance the classes, we trained different instances of what we call RetinaNet, who's a detection model architecture using concatenated images and bounding boxes. Each input image included 1 positive and 1 negative exam that were paired together as a single input. Each input image, this technique apparently helped to improve the classification performance, but with a trade-off on bounding box precision. So Some of our detection models also use a special type of convolution named deformable convolution. The usual convolution neural network are using like tight kernels, but this type of convolution is using a spaced convolution kernel with learnable offsets between the elements of the kernel. So this allows to generate a spatially distorted feature maps that helps to improve the learning capacity of the network. This type of convolution combined with a region-based fully convolutional neural network that is also a detection architecture is reporting state-of-the-art detection performance on many different public datasets, including the well-known COCO dataset. So that's one of the reasons why we choose this architecture. So when we look at the classification networks, we had an average classification AUC of 0.894 on our internal cross-validation. As you see, we used 3 different architectures for classification: exception, inception, ResNet v2, and DenseNet 169. We also trained the models with different image resolution. The softmax layer were also trained differently using 2 or 3 classes. So that was a binary or a 3 classes classifier. The first 2 being long opacity and normal, and the third class used was the other abnormality class that was defined in the labels. So our classifications models were also pre-trained on the NIH dataset labels. So for the detection model architectures, we use deformable RFCN, also deformable relation network. So both of these architectures are using deformable convolutions like I explained before. And we also used a very frequent detection models that is called RetinaNet. They were trained with different folds and different resolution. And we also observed a significant difference of MAP, internal validation score, when we tested on all cases versus positive cases only. So that was the main reason that we decided to combine a global image classification score with a local bounding box score because of this difference. We also observed a trade-off for detection models between classification performance and bounding box precision performance. For example, the best classifier was concat RetinaNet, and this model had the lowest bounding box precision. So these differences between the detection models also explain the benefit of creating an ensemble of models. When the predictions of different models are highly correlated, then you don't really benefit much of ensembling the models. But when predictions are relatively uncorrelated, then the benefit of ensembling is more optimal. We can also give the example of double reading in mammography. If, let's say, 2 readers are always recalling the same exams, then you don't get any performance benefit of double reading. Also, an important step to improve performance of the test set was to adapt the bounding box size according to the difference in the annotation process between the training and the test set. The training set was annotated by a single radiologist, and the test set was using the intersection of bounding boxes drawn by 3 different radiologists. So assuming some inter-reader variability in the annotations, it was relatively predictable that the intersection of bounding boxes would be smaller on average than a single box. So basically, we just resized our bounding boxes by a fixed ratio, and it showed significant improvement on the leaderboard score. It's not really surprising that our 60 model solution was relatively slow. The inference of a single image took 19.1 seconds on a Titan X GPU. After the competition, we made some tests to speed up the inference phase by simplifying the ensemble. We were able to get almost the same performance, test performance with a single Inception ResNet v2 classifier and 5 instances of deformable relation network with an inference speed of 1.5 second per image. So we also, our code is fully available on GitHub, so you can access it on GitHub if you want. And here is our contact information if you have any question about the challenge after the current session. It will be a pleasure for us to answer.
Alex, I know I think we're going to listen through everyone's presentation, then we'll have time for questions now. And just a shout out again to RSNA for the new journal, and one of our future sessions we will have the editors of a couple of journals come in and talk about publishing. So we are going to move on to Dr. Chan.
Okay, can you see my screen?
Yes, I can.
Okay, great.
Yeah, which ones are the okay.
All right, thanks, Judy. It's hard to follow Alex. They just did some pretty amazing work with Alex and Ian together. It's just a few words of introduction about myself. I'm an abdominal radiologist at the Keck School of Medicine of USC. So I spend most of my time on clinical work, but I am very interested in machine learning in my spare time. So prior to this competition, I did have some experience playing with convolutional neural networks for image classification. But this is the first time I had worked on a problem on object detection. And just to be clear, when we say object detection, we mean the task of identifying something in an image and specifying its location with a bounding box. This was also my first machine learning competition, and I entered as a solo team. I think we're all really fortunate that there are so many online resources for learning about machine learning and deep learning. So I just want to highlight 2 resources that were helpful for me when I was trying to start to learn about how object detection works. One is the set of Coursera lectures by Andrew Ng on convolutional neural networks, and the other is the series of fast.ai lectures by Jeremy Howard. And I think both of these are really excellent, and they're complementary in certain ways. So I think people who are interested in some more background, I would highly encourage people to look at those. And in fact, I think from Jeremy Howard's lectures, I learned about RetinaNet, which was basically the architecture I centered my solution around. This is a single stage architecture for object detection. And it basically consists of a convolutional neural network backbone. And it has these layers at different scales that feed into subnetworks that perform both object classification and bounding box regression. And from a practical standpoint, the most important thing for me is that this is a high-performing single-stage network. And I thought that this would be a lot easier to train than the alternative, which, the alternative architecture for object detection is most popularly like a 2-stage system. And Alex showed some examples of this. I think he used several different kinds of architectures, but I was focused just on the RetinaNet. Specifically, my solution was centered around training the Keras implementation of RetinaNet, which is available on GitHub. And for those who are not familiar with Keras, it's basically a framework for deep learning that typically uses TensorFlow as a backend, but it's high level enough that it's relatively easier to use than just using TensorFlow directly. So in terms of preparing the data, they gave us these 25,000 odd training images. So I divided them up into a fairly large training set and a small validation set. I'd actually started with a larger validation set, but over the course of the competition, I found that I would get better performance by just increasing the number of images I had for training. And in order to further increase the size of the training set, I applied a variety of image augmentation methods that are listed here. I think one of the few decisions I made that actually involved some knowledge of radiology was to use the images at a relatively low resolution, specifically at 224 by 224 pixels. The original images were supplied at 1024 by 1024. So this is one of the training images at both resolutions. And I don't know how well this is coming across, but the image on the right is when I'm looking at it, it's clearly more blurry. And I wouldn't want to use it for certain tasks, like if the task was to find a small pneumothorax or a small nodule or some kind of non-displaced fracture. It would be hard at this resolution. But for the purposes of finding and forming a bounding box around pneumonia, the resolution looked sufficient. And this was important to me because operating at a low resolution was a lot more efficient on my training hardware. So when I was training the model, I saved a model snapshot after each epoch, where one epoch represents one cycle of exposure of all the training images to the model. And one of the central questions that I was working on was, when exactly to stop training. You never want to train your models too long because you tend to overfit the training set. And so after each epoch, I would calculate the value of the maximum RSNA metric that I could get by varying the score threshold for the model. By RSNA metric, I mean the evaluation metric that was specified for the competition, which was actually kind of a complex custom metric, which might be worth discussing later. But what was interesting to me was that the best model by this metric on the validation set, here, for instance, it would be around epoch 14 or so. This wasn't necessarily the best performing model on the test set. In fact, I found that a better indicator for test set performance was to calculate a Youden index, which just represents sensitivity plus specificity minus 1 on the validation set. And here I'm calculating sensitivity and specificity with respect to images rather than bounding boxes. So based on this metric, the best performing model would be around, say, epoch 22. And I'm leaving out some details here. I would further tweak the sensitivity threshold to increase, the score threshold to increase the sensitivity, and that improved test set performance as well. And I never really had a good explanation during the competition of why this should work better, but it was an indication to me that the test set statistics were somehow different from the validation set. And along those lines, and Alex has already alluded to this, I think one of the most important observations I made regarding test set performance was that reducing the bounding box dimensions by a fixed percentage significantly improved the test set score. So this is just an example of shrinking the bounding box for one of the validation set images. And in this case, it's not obvious why this should improve the score. Both of them are pretty close to the green ground truth box. But we do have a reason to believe that this is helpful for the test set. And as Alex said before, this was already reported on the Kaggle forums by one of the organizers, Dr. Anouk Stein. And she says that the test set images all had multiple readers, and in particular, the intersection of bounding boxes was used as ground truth. So that would imply that the test set bounding boxes are likely to be systematically smaller than the training set bounding boxes. And I was just looking today at the article in the inaugural edition of Radiology AI And I haven't read the article yet, but I pulled this figure out from, and this was the article by the organizers. And it shows the histogram of the sizes of the bounding boxes for the test set and the training set. And it also shows that there's a shift to smaller sized boxes in the test set. Again, probably because the intersection of bounding boxes reduced the ground truth, the size of the ground truth box. So in the end, my solution is very simple, really. It's probably the most basic solution of the ones on the leaderboard, but it basically consisted of an ensemble of 2 retina nets trained, as I described before, with different backbones. And I took weighted averages of the bounding boxes and then applied that bounding box size reduction. There were, I think we all have lists of things that didn't work. I won't go through all the ones that I tried, but one of the ones that came to mind early was I did try to use information from, say, the DICOM fields of the images as to whether the images were AP or PA. I think many people during the competition realized that AP images were more likely to be positive for pneumonia because they're more likely to be, hospitalized patients. But I never found a way of incorporating that information to improve my performance. And maybe that's because the neural networks were able to somehow incorporate that knowledge of the kind of image that was being analyzed, so that adding that extra knowledge didn't really help. And of course, there are also plenty of things that I didn't try, either because I didn't have time or I just didn't know how to do them productively. But I know several teams did try many of these options, and it just shows that there are many ways of solving the problem. So I wasn't really expecting to do that well in the final aspect of the competition because I had dropped out of the top 10. I think in the last week of stage 1. But I was kind of surprised to see that I moved up in stage 2 of the competition. Part of it may be because I somehow was able to manage overfitting to some degree because my numerical score really didn't change between the 2 stages. But quite honestly, I think there's a lot of luck involved, particularly in the middle of the leaderboard here, where you can kind of see a lot of these scores are really close together. So I think a slightly different test set would have jumbled the list quite a bit. Although I'm pretty sure the top 2 spaces in the competition would have been the same. So just in conclusion, I think that certainly understanding the data is critical for any machine learning problem, and certainly in competition. And for competitions in particular, luck also helps as well. And I just want to echo Alex's thoughts about how this competition is really only possible because of some really dedicated work by the organizers from RSNA and STR. So I'm giving a shout out for their article that just came out today. And my code and models are also available on GitHub. And that's it. So I'll give it back to Judy.
Thanks, Dr. Chan. That was very, very helpful. And we are going to listen to Felipe, who's our last presenter for the evening. And I can see some questions starting to pop up. So please continue asking, and I hope we have actually some good time for a good discussion. Catherine, do you want to make Felipe the presenter?
Hello, good evening, everyone. Can you see my screen?
No.
Okay.
The screen is to me.
So can you see it now?
Yeah, absolutely.
Good.
Okay.
So I'm Felipe Kitamura. I'm a neuroradiologist in São Paulo, Brazil. And I'm also very interested in machine learning applied to radiology. Right now, I also work in a company that is trying to apply AI models in the clinical practice, and we're facing a lot of validation problems. But as far as the competition is I would like to say that this was a huge effort from our team, made by 3 different companies. One of them is DASA, which is the company that I work for now. Fiji, the company that one of the other members work, and also Yara Health. That is mainly the IT and computer science guys are from. So this is our team. We have here José Eduardo Venson and Daniel Souza, Bernardo Hennes, and Alisson Scapinello, which are very bright guys that came up with really interesting ideas that made this result possible. And Igor is also a radiologist that helped us a lot with some of the ideas, and also annotating some of the images when we were trying different ideas. So I'm not gonna go into a lot of details, because I would say that if I had to compare, the solution that we came up with is quite similar to the one that Philip Chang just described. So we used RetinaNet as well. And one of the things that we tuned that we thought that helped a little bit is using different anchor ratios for the anchor boxes. So for RetinaNet, one of the hyperparameters that we have to tune is these ratios, like saying which are the shapes that we expect the opacities will have. And we studied a little bit of the ground truth that we had from the training set, and from this data we chose to use these numbers that are here from 0.25 to 4. So we have about this 1 to 4 ratio from in height and width. And this was something that we saw that helped a lot. And another thing is that we abused from data augmentation, as well as some of the other people already said. So we did a lot of rotations and scaling and shearing and flips. And these ones here in this first item are some kind of data augmentations that we have take care of the output as well, because when we rotate or flip the image, the ground truth, the position of the bounding box has to change accordingly. But we also did some data augmentation that is just done on the image itself, like contrast, brightness, and also adding noise to the images. But if we had to choose one key method that made our results way better than it was before, we would say that is this bounding box reduction in size. And for us, 16% reduction was the optimal number. And we didn't quite understand why that was happening. Alex already explained a reason why, and it's quite simple, and by reading Anouk Stein, as Philip said, one could come up with this idea, but we didn't know that. We just tried a lot of different domain adaptations, and this was the one that worked. So it was mainly, I would say, we were mainly lucky of finding out about this. So other details that may not be that important here, but Alex and Philip also mentioned about the backbone they used as the convolutional neural network for RetinaNet. And for us, the one that worked better was ResNet 101. It's just a detail. If you want to try yourself, you may have to do this kind of choice. And also hyperparameter tuning. And the hyperparameter that was more important for us was learning rate, which is not quite surprising because it's usually the more important learning rate in most of the model trainings. And also during inference, we have to choose other thresholds, like a threshold to define if it's a positive pneumonia case or if it's a negative case. And also the another hyperparameter called non-maximum suppression, which is something like a threshold for us to decide if we're going to consider a bounding box is overlapping significantly with the others or not. So these were other things that we tried to tune. And we also used dropouts on both regression and classifier heads of RetinaNet. So RetinaNet has this classifier head which just tells us if it's a pneumonia or not, and the regression one that tells us where the bounding box is. And dropout is a technique that is usually used to reduce overfitting. So we use dropout on both parts of this network. We also did, like Philip said, we also had some things that we tried that did not work the way we expected. So we tried different architecture backbones like VGG, Inception, MobileNet, and other custom architectures. It didn't work well for us. We tried smaller image sizes, and this is something interesting because we used 800 by 800 pixels. And when we tried 400 or 500, it was way worse. So this is surprising because the result that Philip Chang had was quite different. And we tried using histogram equalization as a pre-processing step, or trying to freeze the first layers and just fine-tune the deeper ones, or classify before using bounding boxes like Alex and Ian did. Also passing additional features like gender, age, view positions, or training different instances of the models for these same features, and they did not work so well. If you want to see our code, it's also available on our GitHub, and we have the Keras RetinaNet, which was the code that we based on. We had to make a little modifications on it, so this is why it's worked here. And we have also the training and inference code that led us to the 10th position. And if you want to try our model with your own DICOM, with your own chest X-ray, you can go to this this URL here, yarahealth.com/pneumonia, and just upload your DICOM. Just don't forget to anonymize before you upload them. We're going to do that anyway. We're going to anonymize it anyway, but it's just good to be sure. So this is a video showing how you would upload your DICOM to get it processed and see the results of the bounding box in Yara's website. I just want to emphasize that this was a team's work, and everybody was very focused on this, and I want to thank everyone in this team for the result we have. And I also want to thank Judy for inviting us to present here today, and also thank you and also congratulate you for this initiative in this journal club, which is very nice. I'm also want to participate in the next ones. and watch what you guys are doing. And congratulate also Ian, Alex, Philip, and everyone else that was in among the winners. So I guess that's it.
Yeah, thanks, Felipe. Really good presentation and nice, catchy. People can have something that they can try out and sort of have a sense of how this works. And so now we have around 20 minutes for questions. I think some asked if there's a way that the winners or RSNA advisors could collaborate as mentors and advisors with a startup in India. I think everyone shared their emails during their presentation, so you can get a hold of them. And know that some of the people on the call, like Safwan, who helped organize the competition. And I think if you reach out to folks offline, you'll get enough people to sort of collaborate with. And this is a good thing because I think we have lots of collaborations that come from panelists and also people on the journal tab. I think we have actually asked, how did you annotate the images differently? And what software did we use? I think this we couldn't get the thoracic radiologist who helped a lot with the annotations. I know Anouk is on the call, and I think it was MD.ai platform that was used for this. And yeah, and then you have another question, and this is going to the panelists. Do you feel like the bounding box reduction importance is a flaw in the validation metric for pneumonia? Because this seems like clinically there's no difference between the larger versus the smaller box.
I can take it, this question. Usually in the competition in machine learning, the training data set and the test data sets are usually almost the same. We are trying to measure the generalization of models. So that's why I called it domain adaptation. When we change the parameters or the labels by different type of annotations or different images or small changes of task, that's what we call domain adaptation. So that's a different challenge. This challenge was mostly a domain adaptation challenge, and it's a good one also to measure the robustness for clinical validation. Because if we want to do clinical validation of our models, we want to see models that can perform on different data sets, different labels, with a certain level of performance. So for this this problem, the main adaptation was like we said about the size of the bounding boxes. That was probably a surprise for the organizers, I should say, because what created this change in the size was mostly the variability of the size, the variability of the annotations. If all the 3 radiologists were always drawing the same box, well, the final intersection would be almost the same size. But what this competition told us is that in classification of pneumonia, there's a relatively high correlation between readers, but for drawing a bounding box to locate the opacity, there's most likely a high variability between readers. So yeah, that's it.
Okay, I have another question. Any idea why 224 by 224 worked for one solution, but 800 by 800 worked for another presenter?
Yeah, I'm not actually sure what I know Felipe had mentioned that he had problems with lower resolutions, and I think I may have used the lowest resolutions among the top teams on the leaderboard. I'm not sure why it worked in one way or not the other. I think for me though, rationalizing why it could work is I mainly tried to convince myself that it was going to work by looking at the images, looking at a bunch of images at a low resolution, and thinking about whether the specification of the bounding box for me would be significantly different. And I had enough confidence that it wouldn't make a huge difference just by looking at the images that I went forward throughout the rest of the competition with just doing the low resolution. And I was kind of limited actually because at trying higher resolutions because my hardware was kind of limited. So I was just stuck at the low resolutions. I never even tried to see whether I might have. It's possible that I might have given up some performance by exclusively using that low resolution.
Okay. So if I may add to what you just said, Philip, if I had to explain why a low resolution would work, if it would, I think the main reason is that it did in your solution. And we tried it, but it didn't work for us. But when trying lower resolutions, we also did the same as you did. We looked at some images and trying to see if the lower resolutions would make the diagnosis harder or not. And we thought it wouldn't, but maybe it's something related to just tuning the model.
Okay.
Maybe one more comment about this is the performance metric that was measured was like Philip said, was a complex measure frequently used in detection competitions, and this measure called the MAP is a mix of classification and detection. Our experience when training models was that lower resolution was better for classification, but higher resolution was better for localization and the precision of the bounding boxes. So basically there was probably like a trade-off depending on the architectures, all the hyperparameters toward one side or the others that could give the same result at the end if you improve on the bounding box precision instead of the classification.
Keep the questions coming. Safwan asks, if you were to give feedback to the annotators, would you have recommended a different methodology or additional information for model development? I'll repeat the question. So if you were to give feedback to the annotators, would you have recommended a different methodology or additional information for model development? Dr. Chan.
Well, I would say that the methodology was excellent. I think they use in this kind of a project, you want to have very clear definition of pathology, to have a low variability of annotations, and the classification results that were way better than the NIH models trained on the NIH dataset showed that the definition of the labels were very good. But the problem was mainly, like I said, about the bounding box precision with the high variability of the bounding boxes. And probably to keep a better link between the training and the test data set, just choosing the average of the three annotation would probably give a better link between the training and the test data set, because for the test data set with the intersection of the bounding boxes, we have not much signal except the size to really improve the result. And we can compare with different other detection competition. The most known is the COCO dataset. COCO is a dataset with 80 different objects with bounding boxes, and the best models on the COCO dataset are scoring about 0.5 to almost 0.6 MAP. which is a lot better than our competition. And that's also proving that the definition probably of the bounding box wasn't that clear for the annotators. But as a radiologist, I could really understand. I can really understand that defining the boundaries of a long opacity is really hard and must be variable.
Okay.
Yeah, I totally agree with you, Alex. I would say that the annotation job was done in a very good way. It was done in the right way. One of the things that I think are very important for that is having a very good tool for that, a tool that allows people to share annotations and adjudicate them. And for that, I think MDAI was like very, very important. And regarding the way that the annotations were done, I don't think they were flawed. I think they were done in the proper way, because as it's a huge effort to annotate all of these thousands of images, you have to choose where to put most of your effort. So having one annotator for each image in the training set, I think was a very wise decision. And having more than one annotator for the test set was also a very wise decision, because you want to have the best test set you can. And you don't need to have the perfect label for the training set. So I wouldn't change anything answering the question that Sefwan.
Yeah, I'd also like to echo that the annotators did an amazing job in this competition. And the one thing I had in mind was the same thing that I think Alex just mentioned, was maybe instead of taking the intersection of bounding boxes, taking some kind of average of the bounding box coordinates might have not caused the systematic size reduction. But I'm not even sure if that's true or not. I mean, that may be something worth checking to see whether that might have eliminated that discrepancy between the single annotated images and the triple annotated images. The other thing I wanted to mention is that this MAP metric that's used for other detection competitions, I think this competition actually was using kind of a different kind of mean average precision. I don't have the website up, but I think the metric was kind of like a custom sort of metric at using different thresholds of intersection over union of the bounding boxes. I'm curious where that came from, because it also made training a little bit less straightforward, because a lot of these models like Keras Retina, for instance, will report mean average precision, but it's not the same kind of mean average precision as the metric used in the competition. So it's actually it was a little tricky. I think one of the things I spent a lot of time doing was trying to think about how I could incorporate components of that metric into, say, the loss function or the training in some way. I don't think I did it in an optimal way, but I think it made it a little more challenging to figure out how that metric works and how to optimize for it.
Okay, that's pretty good. One last question from the audience is, can authors please share details of the hardware the GPU used for training their models? And maybe I'll add one more thing. What was the approximate cost for training?
Well, for us, our team, Ian, with his research lab, he had access to 8 Titan X GPU, which is a lot, and I have personally access to 2 GPU 1080 Ti.
I was using basically a retired PAX workstation that's about 10 years old, but has a fairly modern GPU, a Titan XP that actually was donated from NVIDIA for some other research I was doing. So really, the GPU is the main driver in deep learning. But yeah, I only had the single machine for the competition.
So we had a little more GPU. So we had an on-prem machine with 4 V100, and we also rent some GPUs in AWS and Paperspace. So in total, I don't know the exact number, but we had more than, I would say, more than 20 GPUs running at the same time in the last week of the competition. And that cost about, I would say, maybe $1,000.
And we have some links there about if you want to look at the data set, you can clone it and re-annotate it. So if anyone wants to think around the data annotation, you can share that link. So my last question to you is for anyone on the, on the webinar who is going to plan to participate in a competition this year, what would your advice be to them? Where should they be focusing their efforts on? Now, I know we sort of indirectly went in some of the resources, but how would you, what advice would you give to other people on the call and who would watch this later who want to get involved in a competition? And number 2, what are you excited about the year 2019? Alex,
well, yeah, sure. Well, for the recommendation, I would divide my recommendation depending on if someone is already coding or not. I think we have a very broad audience in radiology, so probably most of the people there are not coding. So what I would recommend would probably be to pair or to find someone interested as a computer scientist, where you can share on one side the domain expertise in radiology, and on the other side the coding ability to do deep learning. And you don't need that much expertise, and that's why that's the message of Jeremy Howard from FastAI, that you probably just need like 1 year of coding experience to start to do deep learning, and he's doing really a great work to democratize deep learning. So that would be my recommendation. If you're already coding, well, I would definitely start with FastAI to learn how to train models. And as Philip said, also deep learning.ai is more a theoretical course, and they are totally complementary. And just try to participate on Kaggle on any, let's say, medical imaging competition, or just imaging competition. That's almost the same skill. So I would say just try as fast as you can to, even if you're not performing very well, you'll learn a lot just by participating in a competition.
I would just add that, and I think Alex referred to this earlier, it does take quite a lot of time if you really want to try to do well on the competition. I mean, I don't want to discourage anybody. It's really a lot of fun, but I had one of the reasons why I hadn't done this competition, these Kaggle competitions in the past, was I never had I couldn't justify the amount of time to spend, but the timing for this competition worked out for me. So. But I would spend a lot of nights and weekends just trying to figure out what was going on and seeing movements on the leaderboard. So it does take a lot of time to tinker with the data for the competitions, but everything that Alex said in terms of getting background material is I would agree with. In terms of things that I'm excited for in 2019, honestly, I consider myself an amateur for deep learning and machine learning purposes. So for me, it's a lot of catching up on technologies that are in the CS literature and maybe sort of getting into radiology. I haven't. I need to catch up on some of the generative models and the work in NLP. I'd like to learn more and see if I can apply some of that to my own work. But it's not necessarily the leading edge. But I'm trying to hopefully get some of the work that's being done in the computer science literature that's accessible. My goal is to try to bring that into to apply that to radiology images.
Okay.
So I totally agree with what Alex and Philip just said. I would just add that as soon as if you plan to participate in a Kaggle competition or RSNA competition, as soon as you have the timeline, I think planning ahead what to do in each stage is something very important as well. And about what I'm excited in 2019, I am more of a deep learning.ai guy, so I learned something with Andrew Ng. And I saw that Alex and Philip have been talking about fast.ai, and Jeremy just announced the 2019 version of fast.ai, so I'm excited to start this course this year.
Okay, thank you. So, well, I'm going to thank you again for joining us. I think there's a lot of material to cover here. I would encourage, if you're listening, just go back and listen again. I do the same and just read some of the new concepts that you've had. And this is the thing, if you sort of keep learning something every time, we will all get better as radiologists, whether you want to be actively developing the models or just supervising their deployment. And I really wish to thank the panelists. This would not happen without you, and so thank you. And yeah, there are lots of people on the chat saying thank you, this was amazing, so thanks again. And so a recording will be available. You'll get copied in the email when the recording is released. I'd also like to thank Catherine, the staff from the ACR who helps me and coordinates a lot of emails and things to get these things moving. So have a good night, and hope to see you next month.